This is also a combustion reaction. This is called nitromethane. So now we've got carbon, hydrogen, oxygen, and nitrogen, and we're doing a combustion reaction. How are we going to solve this? Where do you want to start? Now, you've got a couple of choices here. Certainly where to start, that's easy, but where to finish, you've got isolated oxygen and you have isolated nitrogen. But let's not worry about those yet. Let's go ahead and start with the ones that are present just in one material on each side. That's either going to be carbon or hydrogen, it looks like. So let's start with the carbons. I like starting with carbon. So we have one carbon on the left and one carbon on the right, so there, right? The carbons are balanced, so we don't need to do anything here. What about the hydrogens? Now that's a little trickier. We've got 3 on the left and 2 on the right. Now you don't necessarily want to use a fraction here because we're just starting off, right? You could also go back to that exercise that we did with ions. Remember when we're making ionic compounds and one has a +3 charge and one has a 2- charge, and you know how to mix those together, right? You find the lowest common multiple. So we know then for the hydrogens, we're probably going to need 6 hydrogens on both sides, at the very least. That would balance the hydrogens. If I have 3 on the left and 2 on the right, then if I put a 2 here and a 3 here, I've balanced the hydrogens. See that? I guess that's another little trick. Now, because I did that, the carbons are no longer balanced. So now let's go back and balance the carbons. I have 2 on the left and I have 2 on the right. Okay? So now the carbons and the hydrogens are balanced. We're left with nitrogen and oxygen. Now oxygen is present in multiple materials, so we really do want to save that one for the end, even though both oxygen and nitrogen are isolated. So let's go ahead and balance the nitrogens. On the left, we have 2 nitrogens. Oh, look at that. On the right, we have 2 nitrogens. So the nitrogens are balanced. So now there's nothing left to do except to balance the oxygens. We have 2 times 2 is 4 oxygens over here, plus 3 gives us 7 oxygens on the right-hand side, and we have 2 times 2 is 4, plus 2 is 6 oxygens on the left. So we use our fraction. What's the fraction going to be? Where's the fraction going to go? We already have 4 here. We need 3 more. So yeah, you need 3 over 2. That gives you 7 overall. See that? So now we can multiply through. That's going to give us 4. This goes away to 3. This becomes a 2. This becomes a 4. And this becomes a 6. Okay? That should be the answer. Let me just go over this idea really, really quickly, all right? Because I think it really does set the stage for understanding the math that we do on theoretical yields and limiting factors. So here's the tricycle example. Let's build tricycles. Let's just call them trikes, so I don't have to write tricycle all the time. What's the molecular formula for a tricycle? Well, we need to know what the parts are, right? What are the atoms in the tricycle? What do we got?
3 wheels.
We got 3 wheels, all right? What else do we have? One seat. Chassis? Is that what you said? Chassis. That sounds really classy. How about a frame? Is that what you meant? Yeah. Okay. What? How many frames? 1 frame. You said seats.
Yeah.
How many seats?
1.
1 seat.
2 pedals.
2 pedals. All right. Let's stop there. That's good. That's what I like. All right. So that's our chemical formula. I guess if I was really careful, I would put them in alphabetical order, but let's not worry about that. All right. So that's the molecular formula. We can write what the equation is that builds this. Right. It's a combination. Right. We have 1 seat plus 1 frame plus 3 wheels plus 2 pedals gives us a tricycle. Now, we're in the business of building tricycles, so let's look and see what we have in the warehouse. So in the warehouse, we have, let's see, I have to write this down. Let's say we have 50 frames and 100 seats and 60 wheels and 50 pedals. The question is, how many tricycles can we make? Now, you had me for lab, don't answer the question. You might not be able to see it. Did anyone see what the answer is just by looking at it? Nobody? Not in my lab. Not in my lab. Yeah.
30.
30. Why 30?
Because you take your wheels and you divide it by 2.
Because you take the wheels and divide it by 2. Why are you dividing wheels by 2?
It takes 2 wheels to...
Oh, but this is a tricycle.
Oh,
We've got 3 wheels. But it's the right idea. Let me show you the thorough process of figuring this out, because that's going to model what we're going to do with real chemistry. Right? We take a look at how many tricycles can we make from the 50 frames individually, assuming everything else is not limiting. We have an unlimited amount of everything else. If we're limited by frames, we know that there's 1 frame for every tricycle, so we can make 50 tricycles if everything else was available. Okay? And we do the same thing for seats. From 100 seats, well, there's 1 seat for every tricycle. So from 100 seats, we can make 100 tricycles if we had all the other materials. For the wheels, right, we need 3 wheels for every tricycle. So we can only make 20 tricycles from the 60 wheels. And the pedals, we have 2 pedals for every tricycle. So we can make 25 tricycles from the 50 pedals. Right now, each one of those computations was assuming that everything else was unlimited. But it's not, okay? Here's the equation, right? We stop making tricycles once the first material runs out completely. Which means that of these possibilities, we can only make the fewest amount of all the possibilities. Because once that runs out, we can't make any more. Which means that we can only make 20 tricycles. But you have to look at each individual possibility to find out. And then you can only make the fewest, because that's telling you what's being it's telling you what's limiting the reaction. So to be specific about these terms, the limiting factor, this is what runs out first. And the limiting factor, because it runs out first, that then determines what the theoretical yield is. And the theoretical yield is how much you can make. Now, a common mistake that students make when they do these is they figure out all the individual possibilities, and then to come up with what the theoretical yield is, they add them all up. 150, 195. That's wrong, okay? Don't be that student, right? You have to do all the individual possibilities to see which one gives you the lowest amount. And then you can figure out, well, okay, now I know the lowest amount has to be the theoretical yield, because that was determined by the lowest amount because that ran out first. In this case, the 60 wheels are all going to run out before any of these other materials run out. Okay? Now, let's say we want to make a profit here, and tricycles just aren't doing it for us. So let's, from the same inventory, we can certainly make a lot more bicycles than we can tricycles, right? What's the molecular formula for a bike? That's going to be 1 seat, 1 frame, 2 wheels, and 2 pedals, right? So from the same 60 wheels, we now have 2 wheels per bike, we can make 30 bikes instead of 20. So let's say we switch our operations and make bicycles from this inventory. How many bicycles can we make?
5.
I hear 30, I hear 25. Who thinks it's 30? Who thinks it's 25? Ooh, it's 25. Why is it 25? Because wheels are no longer limiting. Because we changed operations, we make 30 bikes, but we still make 25 from the pedals, 150. So now pedals become the limiting factor. The limiting factor is what runs out first, and that determines what the theoretical yield is. Okay? These are definitions, but you have to understand what the definitions are defining. You've taken 2 of my exams now, and you know that some of the questions are simple definitions. It's not just knowing how to do the hard computations, but it's also knowing what the simple definitions are. All right? Sometimes students, including you all, don't keep track of the simple definitions. So here's 2 more for you to keep track of. Know what they are and know how they interplay. Okay? So now that you've had that fun example, let's do a practical example now. Now we're going to ask how much H2O gas can be produced when reacting 4 grams of the nitromethane and 3 grams of O2. So let's put that in here. Now we've got 4 grams of this and 4.00 grams. 4.00 grams of this and 3.00 grams of that. And we want to ask how many grams of the H2O can we make? Simple enough question, right? And we're going to go through it step by step. There's a lot of math on this slide. So lots of white space, so we're going to do a lot of math. But it's not anything that you haven't seen before, right? It's mostly just dimensional analysis, which we've done over and over and over again. But students do get confused by this, so I'm going to go over it very slowly, even though you've already done this in lab, okay? So, first of all, these coefficients in red, are these mass ratios or molar ratios? They're molar ratios. Okay? So even though we have 4 grams of one and 3 grams of the other, what do we need to do? Say it loud. Convert to moles. We need moles. So how do we convert grams to moles? What do we need? It's not Avogadro's number. You need the molar mass, which means we need to add it all up. Ugh. Well, fortunately, I did it for you. All right. But let me just show you what you need to do. So for nitromethane, you need 1 carbon, that's 12.011 grams per mole, and we have 3 hydrogens, that's 3.024 grams per mole. We've got 1 nitrogen, that's 14 points, what is it? Yeah, I'm just going down to 2 decimals here. 007. Or sorry, 3 decimals. And what's left? 2 oxygens. That's 15.99. 2 of them. 31.998. Right? And you add all those up. And you should get, I'll just tell you, so that we don't spend time on this, we should get 61.04 grams per mole for nitromethane. And for molecular oxygen, well, we know what that is. O2, I already calculated it for you. That's 31.998 grams per mole. Okay? So now we have those numbers. Now we just do dimensional analysis. Here, there's a 0 here too. Now, just like with the bicycles and the tricycles, we need to do each one separately and then see how much H2O we can make. And then we'll know, once we do both of them, that the amount that we can make, the theoretical yield, has to be the lowest of the 2 because of how the limiting factor works out here. Okay? So let's first convert into moles. So we have 4 grams of nitromethane, CH3NO2. That's our given. Our conversion factor is going to be the molar mass, so we can get this into moles. And we just calculated, we have 61.040 grams of C3NO2 per 1 mole of C3NO2. Now, I'm being very careful to put every single part in each term. The units and the units of what? Because we need to keep track of when we're going from one compound to another compound. If I were to stop the calculation right here, we would just calculate the moles of nitromethane. But I want to go all the way over to H2O. You've seen this before, right? And in lab, you did it step by step. I'm going to just show you everything in one large dimensional analysis, keeping track. And one of the biggest mistakes that students make when they do this is they try to merge too many things into one conversion factor. Keep it separate, keep it clean, and notate everything. Don't be that student who makes that mistake. Okay? So what's the next term going to be? Will the units be in the denominator of the next term? We want them to cancel out. So we already calculated moles of nitromethane, so that's what's going to be in the next term. And we're going to convert that to something else. Now, what's that going to be?
Moles of water.
Moles of water. Sure, that sounds good. Because we want to know how many moles of water we have, and if we know that, then we can convert it into grams. So what is the relationship between moles of nitromethane and moles of water?
6 to 4.
It's 6 to 4. That's where you use the molar coefficients. But don't reduce that fraction. Keep the numbers the way you have them balanced. That way you can keep track of everything that you're doing. From the balanced equation, there are 4 moles of nitromethane for every 6 moles of H2O. If I were to stop the calculation here, we would calculate how many moles of H2O we have. We want grams. So let's go one more step. We need moles of H2O are down here, and we're going to have grams of H2O up here. That's the molar mass of H2O. Now, what is that? Anyone remember? We can calculate it out if you want to. But we want 3 decimal places. So 18.015 grams per mole. And then we're going to get some number. Let's not worry about what the number is right now. Let me be clear about all of these terms. This is what's given. This is the inverse of the molar mass of one compound. This is the molar mass of the other compound. And this is the molar ratio of one compound relative to the other compound. And here it all is in living color. All set up in one expression, so you don't have to worry about making calculator errors and early rounding. You just plug it all into your calculator just the way it's drawn out here. Whatever's in the numerator, you're multiplying by. Whatever's in the denominator, you're dividing by. I wouldn't even suggest you just multiply everything in the numerator and then separately multiply everything that's in the denominator, and then in a third step, take one and divide it by the other. It's just more opportunity for you to make a silly error in the calculator or do some early rounding. It's all here. So the operation is here, I'll just show you with my highlighter. The operation is you take 4 and you multiply it by 1 and you divide by 61, and then multiply by 6, divide by 4, multiply by 18.015. My notes say that this answer should be 1.77 grams of H2O. Okay? Now, you calculate what it would be if we used all of the 3 grams of O2. Set it up. Calculate it out. All right, I've given you all a head start, so keep working on it, and to save time, I'm just going to start writing it out here. All right, I got all the terms up here except for one. the magic one, the molar ratio. What's the molar ratio going to be in this case?
Number 3.
3, that's right. And what goes in the numerator?
Oxygen.
6, no, it's not oxygen. 6 moles of H2O for every 3 moles of O2. Okay? All the units cancel out to give us grams of H2O. In fact, let me emphasize that. All of these units, that cancels with this. Moles of this cancels with moles of that. We converted to moles of H2O, cancels with moles of H2O. And so on and so on. My calculator says that if we use all the oxygen, assuming that nitromethane is in excess, if we used all the oxygen and that were the limiting factor, we would get 3.38 grams of H2O. So we have two options. What is the limiting here? Here's choice 1, here's choice 2, and choice 3 will be adding them up. What's the answer? 1, 2, or 3? If anyone holds up 3, you can leave right now. Okay? You've just made that mistake. You can get out of here.
I bet.
Right? 3 is absolutely the wrong answer. You don't add them up. Okay? It can only be one or the other, as dictated by whatever runs out first. And the logic of it, right? That's the logic of the bicycles and tricycles. You do each one separately, you can only make the lowest amount, right? So that means we're only going to make 1.77 grams of H2O. So this is, by definition, the theoretical yield. What is the limiting factor? Is it 1, O2, 2, C3 and O2, or 3, CO2? What's the limiting factor? 1, 2, or 3? Better not be 3. Everyone's saying 2. Why is it 2?
The lowest amount of water.
Yeah, it produces the lowest amount, logically, all right? That means that we used all of the 4.00 grams of nitromethane to give us the lowest amount. That means, by definition, it has run out. So what's in excess? 1, 2, or 3? 1 is in excess. We could, if I wanted to, if you want to, you could calculate how much O2 is left over. We're not going to do that, but you could. It's simple dimensional analysis. Once you know what the limiting factor is, then you can figure out anything else that you would be asked. You can figure out how much oxygen is left. You can figure out how much carbon dioxide is made. You can figure out how much nitrogen gas is made. You can do it all. All right? It's just more. It's just more of the same. Right? This is the math involved.